Okay, let's go on. Find the largest palindrome made from the product of two-digit numbers, or of three-digit numbers. So what is the three-digit number? It's a number from 100 then to 999. Actually, moreover, I would like to iterate from I plus 1 because it is faster. From I because it is faster. And one more. Since we are only interested in the maximum number, here I don't need very small numbers. For instance, I can start with something like ans over I. Yeah, because if my number is less than ans over I, then their product will be no more than ans. And I'm not interested in it. If it is palindromic, then I say that ans is maximum of ans and I times j. And finally print ans. And let's check that a number is palindromic. To do that, we include string. We put it into toString. We find the reversed string. We just check that s equals a string of s.rbegin, s.rend. Should work like this. Okay, so there is no input file. We just run it. Okay. It's a nice palindrome out there. Let's submit. Okay, problem 5. 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. This is called LCM of these numbers. And we are supposed to find the LCM of numbers from 1 to 20. Okay, the most brainless way is to just write the function LCM and use it. No. Instead, we can create a new project. We remove this, we copy this, we remove this, we print this. Okay, since 20 is a parameter, let's add it as a input file. Great. So okay, so let's go. We write a function LCM. And it is known that to find it, you need to return this number, where GCD will be found by usual way, in a usual way, which is while b, a percent equals b, and swap ab, and return a. However, this can overflow in some bad situations. So what we need to do instead is multiply after dividing. So this is what we return. And finally we read n. And in the cycle we replace ans with LCM of ans and I. Yeah, I believe that's it. No, we need the fifth file. And the fifth output is nothing. Ah, this is because I should have printed it. Also, I realized that I would like it to be in separate directories, so I don't want it to be here. This is a mess. So instead, let's create a new directory, which will be called outputs. Okay, let's just call it txts. And here we will have dot 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 txts and this. Okay, let's check that it worked. Yes, like a charm. But one is not what I particularly like. Because I didn't have the input file. Yeah, so let's cut it from here, paste it here. And we print 20 here, of course. And now it's fine. It even fits in the int, which I didn't expect. Should it fit in the int? I actually don't like that it fits in the int. It shouldn't have. Okay, I will believe it. I will believe it. What is evenly divisible? Divisible with no remainder. Okay, this should be this number. Nice. Problem 6. The sum of the squares of the first 10 natural numbers is this. The sum of the sum of the square of the sum of these numbers is this. And we find the difference. Okay, again, we can find some pretty nice formula, but I don't see a reason to not just solve it in a normal way. Hmm. One hundred. Okay. So what do we do here? We read the number n, and we find the sum of the squares of these numbers and the square of their sum, and we subtract them. So we have sum and sum of squares. And in the end we print sum minus sum times sum minus sum of squares. This is some random number, we print it. Okay, it's still very dull. Okay, find this number, the prime number with 10,000 first index. Actually, I believe I understand why it's written like this, because otherwise it will be Googleable kinda easier. I will check it right now. So first of all, let's add one more source file, create a new project. Here we read a number. Wait, what? Ah, I need to save it again. I read a number and then I find some prime number. Okay, to do that I need some eratosthenes sieve. It can be implemented in linear time. Okay, let's just do it in linear time actually. So to do that we create a vector of primes. And minimum divisors. Great. Let's just create some natural bound of 200,000. And we fill it with ones. Okay, let's go. We start with 2. So first of all, we check, is it true that minimum divisor of I is 1? If it is, then we need to push a new prime. Moreover, I would like to say that if primes dot size is now greater or equal than n, we break. And after that, we need to print it. Okay, what happens here? Here we need to say that any number y is just minimum prime of y times y divided by minimum prime of y. And we now check all numbers. So for a prime number, this is 1. For a prime number, this is 1. For any other number, this is not 1. And we consider now all numbers for which this is I. What does it mean? This means that we need to consider all numbers for which minimum prime is at most minimum prime of this number. So for int j in primes, first of all, we say that if j is at least minimum prime, if j is greater than minimum minimum divisor of I, we break. Also, if j times I is greater than or equal than n, we also break. Otherwise, we say that the minimum divisor of I is simply j. Okay, and for sanity check, let's just print all prime numbers which we meet during the process. Finally, you choose the prop 7 and run it. 2. 2. Really? This is because I needed to write some number here. Okay, this was kinda slow. For some reason it thinks that every number is a prime number, which is nonsense. Ah, because I times j has this mean divisor. Let's fix ourselves. No, it still thinks that every number is a prime number. Now I don't like it. Hmm. For example, let's consider 2. When I say 2, it checks that its mean divisor is 2. It's indeed 2. We push in primes. Then we do something here. We consider all primes. So we're starting with 2. Ah, this happened because I needed to write it. There are 2 ways actually. First way is I can just use some infinity number, for example n, and put it here. But actually the better way is what I need to do anyway is say that minimum divisor of such number is simply I. So now it will work. Yeah, now it works. So I believe that you can just Google this number, and this is why they decided to not choose it. Yes, it is 100,000th number. Oh, understandable, but we will choose the next one. Also, is it really so slow? Why is it so slow? What if I don't print it? Still, it's too slow. I don't understand. Maybe we can try to measure its time. So let's measure the time. To measure the time, we include chrono, and we measure 2 moments. Starting, which is like this, and the finishing one. After that, we print end minus start divided by 1 millisecond and say that this is the number of milliseconds. One millisecond elapsed. Okay, this is not much. And this is not much either. Well, and this is not also much either. Okay, let's believe that this is fine. And we just submit the answer. Okay, the 4 adjacent digits in the 1000 digit number that have the greatest product are 9 times 9 times 8 times 9. Find the 13 adjacent digits in this number that have the greatest product. What is the value of this product? Okay, let's input it. I could reformat it into a single string, but I will not. I save this file. I copy this file. I will not remove the calculation of the duration. It will stay with us. So how do I approach this problem? I needed to not remove this. Okay, let's make this function solve problem. Which does the following. It reads the input and prints the answer. So string s and finally we print find answer of the number. Okay, so we have, is it int? 13 adjacent digits. So 13 digits might be as big as 9 to the power of 13, which I believe can be big. So let's return long. Okay, we can do it the dumbest way possible. So if we consider this, this will be one digit. Actually, let's put 13 in the beginning, which means that we consider only 13, only the strings of length 13, and we will start with 4, so as we can check our answer. So here we say constant equals 4, and here we put it here. So if k is 1, we need to do it until s.size minus 1. So this means I can write this and this. Okay, now I do the following. I take s.subster, starting with I and moving k digits. Now, then I take sister. Then I need to use a toy of the string, and this is the number. But because it can overflow, I will use... No, I actually don't need to do it. I instead need to multiply the digits. Okay, let's not use a toy, let's just multiply the digits. So I say long j equals 0, long product equals 0, 1, or in j equals 0, j less than k plus j, product multiply equals s I plus j minus 0. Then answer is maximum of answer and product. And return answer. And here answer is 1. First of all, let's check this thing. And it clearly says that I didn't run the needed executable. What now? Oh, I messed up this file. Let's rerun the 7th so that we are not sad and afterwards. Then we go with 8. Now it should generate a new output file, which is this. Yes, this is fine. Let's now replace with 13 and we get the answer. We got the same answer. Ah, this is because I needed to read this number. Let's try again. We start with 4. With 4 I said. This is fine. Now I take 13. And this is a bit bigger. And as we see, yes, we needed to use long. For now, this is not a lot of mathematics. And these problems are somewhat dull. Okay, a Pythagorean triplet is a set of 3 numbers for which this happens. There exists exactly one Pythagorean triplet for which a plus b plus c is 1000, and we need to find its product. Okay, this is a problem which if it is implemented incorrectly in Python, it will be taking a lot of time. However, we are users of C++, so we don't bother such problems, we just iterate. 444. Input 0009.txt 1000 prob 0009.cpp not apply, fix this thing, save, nine. Okay, so we read n and we print. Actually, I'd like the find answer to be the triplet, so let's make a tuple of int. And here we will use our order xyz equals this find answer. And I would like to print their product. But after all, I would like to print in the error stream the numbers themselves. Just for the debug reasons. Okay, let's go. This is kind of straightforward. We go for x from 1 to 1000, or from to n actually. Let's go to n or even to n. Okay, so it's easy to see that since the sum of this number is 1000, the minimum of them is at most n over 3. So this is where we stop. Then for int j equals y equals x plus 1, y is at most n minus x over 2, I believe. Is it fine? Yeah, it seems okay. We take int z equals n minus x minus y, and if x times x plus y times y equals z times z, return x, y, z. And here we return minus 1, minus 1, minus 1, just to indicate that we failed. So this was the 9th problem. We run the 9th problem. What did it print? Ah. Is it kind of known triple? Let's divide it by 25 and it becomes 8. 8, 13, and 15, or what? No, 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 no. 8, 15, and 17. Yes? Yeah, it seems like it's 8, 15, and 17. $225 plus 64. I didn't know that there is such a Pythagorean triple. Okay, I will know. Confirmation code this time. What if I am a robot? But okay, let's just print the answer. The answer to the 9th problem is correct. My life will be as sweet as a chocolate bar. Okay, find the sum of all the primes below 2 million. This is quite straightforward. We just use our code from problem 7. We use this template here. We use this here. We print 2 million here. And we just run the sieve. Okay, let's find the answer. To do it, let's just write capital N here, and finally we just, instead of counting this thing, we return the sum, where the sum will be calculated all along the process. So here we say that here we remove this check. We say that sum plus equals I. We remove this. We remove this. And I guess that's it. We just run program. Here I needed to print the answer. Just print the answer. No. See out. Okay, this nice number. Now I'm a decathlete. Largest product in a grid. I don't see a point. Why would you give such a problem? This is simply not interesting. I mean, like, even Python, you just take the one number here and check this for rows. This one, this one, this one, and this one. So you spend 400 times 4 times 4. Like 400 times 16, which is is it only like 6,400? So it's like works. It works in an instant. I don't see a point in such a problem. Should it teach something us? I don't think so. Let's add number 20 so that I don't need to calculate the size of this grid. And let's add number 4 so that this is a parameterized solution. And we add, oh no, what did I do? Now I do it here, and that is basically it. I only need to calculate some products. So how do we do it? Iterate over all beginning numbers. Which are here and here. We check 4 things. So first of all, if I is at least, let's also store number n. So if I is less than n, if I is at most n minus k and j is at least k minus 1, then we create a variable for product. And product is multiplied by vi plus u j minus q. And answer is maximum of answer and product. After that, we just repeat it a lot of times. First of all, let's make the diagonal move, for which we also check it like this. And here we add q. Also, we check the vertical move, for which we simply do this and this. And finally, the horizontal move, for which we add q to j. That's basically it. What does it say? 0. No, it shouldn't be 0. I didn't read the array though, so it should be 0. Nice. Why is it release with debug info? I didn't ask for that. Let's fix it. So here I need to choose just release. Okay. Okay, now it should be even faster than it was. Okay. So it's like 70 million. Does it actually read these numbers correctly? Because it seems that maybe it could be not the case. Okay. Problem 12. Highly divisible triangular number. What is the value of the first triangle number to have over 500 divisors? Okay, to find the number of divisors, we could actually use the my god, we could actually use the Eratosthenes sieve, but I believe it's not the best way here. We can just check everything in square root of n time. So here we need to read 500. one integer input, one integer output. Okay. To do that, we just iterate over all triangular numbers and check them one by one. How do we do that? First of all, we need to find some triangular number. Okay, let me think. In principle, there is a way to use our brains, but I will not use it at all. So the number is simply I times I plus 1 over 2. Then I find the number of divisors, which is called tau, I believe. And if d is at least n, I return m. And that's it. So let's calculate tau. So it's done in square root of n time. How is it done? We check, is it true that n% I is 0? And I start with 2, of course. If it is, then we found new prime divisor. So we say that LL u equals 1, and while n% I equals 0, then plus plus u and n is divided by I. In the end, we say that answer is multiplied by u. If you're interested why is it true, you can check the formula for tau, the number of divisors function. It's called maybe Euler's tangent function or something like this. Or just tangent function. Okay. And to apply it, you need n in multiplicative form. So you need it as a product of pi to the power of alpha I. And the answer is product of alpha I is plus 1. Okay, so we just return once. Let's see how it goes. And of course, it was really fast. Over 500 divisors, so I need actually greater than this. Maybe there is a number with exactly 500 divisors, in which case it would be funny. I almost submitted the incorrect solution. However, it was not the case. There was exactly this number. Okay. Ah, of course. As always, I didn't think before submitting, and here actually if n is greater than 0, n is greater than 1, then I also need to multiply it by 2 because there is one more prime divisor. And if I do this, I believe this number will get smaller. Yes, it becomes smaller. But now it should be correct. Yes. Large sum. What? Work out the first 10 digits of the sum of the following 150-digit numbers. Okay. It should be easily done with Python. but I would like to do it in C++. So let me think a bit about how it's done.